Yeah, you should start recording now and
All
see
right.
what. Yeah, I
All
think
right.
it works.
All right. So I'll just start now,
Yeah.
since I started recording. Okay, so we're going to cover section 13.6, which is cyclotomic polynomials and extensions. So the purpose of this section is to prove that the cyclotomic extension Q adjoins zeta n over Q generated by the nth roots of unity over Q is of degree phi of n. So we're trying to show, the purpose of the section is to try to show that the degree of this field extension is phi of n. So what is, so let me just remind you, what is the nth cyclotomic extension, right? So first of all, zeta n is a primitive nth root of unity, meaning zeta n to the n equals 1. So that's what it means to be a root of unity. And for it to be primitive, you need that zeta n to the k does not equal to 1 for any k less than n, right? So for example, 1 is not a primitive nth root of unity, but e to the 2 pi I over n is a primitive nth root of unity, right? Okay, and then next thing is that the Euler-Tauschen function phi of n, so this is the number of integers a less than n and greater than or equal to 1 that are relatively prime to n. So this is the order of the multiplicative group of the integers mod n. So, okay. So that's primitive nth roots of unity and the Euler-Tauschen function. And we're trying to prove that the field that you get by adjoining a primitive nth root of unity has degree phi of n over q. Okay, so let mu n denote the group of nth roots of unity. And so we notice that this mu n is isomorphic to z mod nz. So on the left, you have addition. So these are the equivalence classes or the residue classes mod n. So you add them and you get the remainders, right? So like n plus m or a plus b mod n. So that's the operation here. And then here, you're just taking the nth roots of unity. So these are these numbers going around the circle. And considering it as a group under multiplication. Right. So these are isomorphic, and the isomorphism is given by you take an integer a and map it to zeta n to the a, where zeta n is a fixed primitive nth root of unity. So there are precisely 5 n primitive nth roots of unity, since zeta n to the a is primitive if and only if a and n are relatively prime. Right. So if you think about it, like if okay, so say this is your fixed primitive nth root of unity, e to the 2 pi I over n. Notice that when you raise this number to the n, you get 1, right? And say that so consider any other nth root of unity, it's going to be a power of this primitive nth root of unity, right? And if that power has some factors in common with n, then you could raise that other number to a certain number to get 1, and that other number would be less than n, so it wouldn't be a primitive nth root. So yeah, this is a fact about cyclic groups, right? And then notice that D is a divisor of n, implies that the primitive or the group of dth roots of unity is a subgroup of the nth roots of unity. Right. Okay, so are there any questions about this stuff?
I'm good with this.
Okay. So, all right. So now let's define the nth cyclotomic polynomial. It's going to turn out that this is the minimal polynomial for a primitive nth root of unity. But okay, so first let's define it. The nth cyclotomic polynomial phi n of x is a polynomial whose roots are the primitive nth roots of unity. So the definition of phi n is you're taking the product over all monomials x minus zeta, where zeta is a primitive nth root of unity. In other words, it's a product of x minus zeta n to the a, where a is co-prime with n. Because I said like the primitive nth roots of unity are just the powers of a primitive of fixed primitive nth root of unity, where you're taking powers that are relatively prime to n. So this nth cyclotomic polynomial has degree 5n and is monic. Well, yeah, it has degree 5n because you're taking products of 5n monomials. And then it's monic because all of these x's have a coefficient of 1. So the leading term, the x to the 5n, has a coefficient of 1. So we get this. And then what I want to say, the lemma is that the cyclotomic polynomial 5n is actually a monic polynomial with integer coefficients and has degree 5 of n. All right, so I could go through the proof, but I think it would be instructive to compute some examples of 5n. So I'm going to do that first. All right. So okay, so let me just do some examples of cyclotomic polynomials, right? So these are examples of cyclotomic polynomials. Right, so first of all, what is phi 1 of x? Well, so you're taking the product of the monomials x minus a primitive nth root of unity. So here the n is 1, so these are the monomials x minus 1. So 1 is a first root of unity because 1 to the 1 equals 1, right? And it turns out that that's the only nth root of unity. Okay, so what about phi 2 of x? Now, all right, so this is going to be the primitive second roots of unity. So, all right, what are the roots? What are the second roots of unity? Well, you have 1 and minus 1, because 1 squared equals 1 and minus 1 squared equals 1. Well, 1 is not a primitive second root of unity because 1 is already a first root of unity. So minus 1 is the only primitive second root of unity. So here we're doing minus the minus 1 because minus 1 is the primitive second root of unity. So in other words, this polynomial is x plus 1. All right, now let's do something. Let's compute phi 3 of x. So here, what are the cube roots of unity? First of all, you have these numbers, right? You have 1, you have omega, and then you have omega squared. And omega and omega squared are both, primitive cube roots of unity. So this is just x minus omega squared. Okay, but notice here I said that this lemma says that the cyclotomic polynomial phi n of x is monic polynomial with integer coefficients, right? This thing, omega and omega squared, they're complex numbers. So what I'm saying is that when you multiply out these terms, you should get a polynomial with integer coefficients. So how can we see this? Let's actually go back to the polynomial x cubed minus 1. Right. So this is going to have right. X cubed minus 1 is going to have so it's going to be a product of the roots x minus 1, x minus omega, x minus omega squared, right? In other words, this is a product of phi 1 of x times phi 3 of x, right? So yeah, you're looking at all of the divisors of 3. So the divisors of 3 are 1 and 3. Both of these things are divisors of 3, or factors of 3. And so the roots of the third roots of unity are going to consist of the primitive first roots of unity and the primitive third roots of unity. There's exactly one primitive first root of unity, and there are exactly two primitive third roots of unity. So these two factors give you this polynomial, and this single factor gives you this polynomial. So any of these polynomials x to the n minus 1, you can factor them as a product of cyclotomic polynomials, but let me just stick with this example for now. So you have this, and then that tells you that phi, okay, let me get the blue color, that phi 3 of x is, we take this polynomial x cubed minus 1 and then divide it by this polynomial phi 1 of x. So in other words, it's x cubed minus 1 over x minus 1. So this is a way to write the third cyclotomic polynomial. And then using long division of polynomials, you can see that this is equal to x squared plus x plus 1. So, and also if you carry out this product like you do FOIL, you get x squared plus x plus 1. You need to know something about the relations, right? So omega cubed equals 1 or something like that. Or yeah. So what I'm trying to say is that phi 3 of x is also a monic polynomial with integer coefficients. In general, you're going to have x to the n minus 1 is equal to the product over the divisors of n, phi d of x, right? Because any nth root of unity is some dth root of unity for some d, some primitive dth root of unity for some d a factor of n, right? And so in this way, you can actually compute the cyclotomic polynomials by doing this inductively and doing long division. And yeah. Let me do another example just to. Okay, so I'm going to do phi 3 of n now. So phi 3 of x, or no, I mean phi 4 of x. Right, so what is this? So first of all right, so I want to compute this polynomial. So first of all, x to the 4th minus 1. This is a product of phi 1 of x times phi 2 of x times phi 4 of x, right? Because the divisors of 4 is 1, 2, and 4. And then, so from this, we conclude that phi 4 of x is x to the 4th minus 1 over x minus 1 times x plus 1. So this is You do long division, you get x squared plus 1. So so that's how you can compute these cyclotomic polynomials. You use the previous computations and divide, and you do long division to compute. Right. I can write out a few more examples of these things. So phi x is x to the 4th plus x cubed. So whenever this is a prime, you're just going to get this whole product, because x to the n minus 1 over x minus 1 is just the sum, right? So x plus 1. So notice that this also had the same pattern. Now phi 6 of x is x squared minus x plus 1, because you're dividing x to the 6 minus 1 over phi 1 of x, phi 2 of x, and phi 3 of x. Those are all the factors less than 6 going into 6. And yeah, so you can make the whole list, but now I'm going to prove in general that the cyclotomic nth cyclotomic polynomial is a monic polynomial with integer coefficients. So we saw a bunch of examples where we got integer coefficients, but now I'm going to use induction to prove it in general. So we already know that phi n is monic and has degree phi of n, right? So this was by definition of the nth cyclotomic polynomial. Now we want to show it has integer coefficients. So we're going to use induction. First, we have the base case. The first cyclotomic polynomial has integer coefficients. X minus 1 has integer coefficients. Now, induction step, assume that phi d of x, so the dth cyclotomic polynomial has integer coefficients for all d less than n. So this should be less than. Right, okay. So for all d less than n, assume that this has integer coefficients. Okay. Now what? Okay. I need to erase. Okay, so we have that x to the n minus 1 is a so yeah. So like I showed in the examples above, you have that x to the n minus 1 is a product of a bunch of cyclotomic polynomials, and these cyclotomic polynomials, hold on, x to the n minus 1. I need to put on the highlighter. All right, so x to the n minus 1 is a product of a bunch of cyclotomic polynomials, and one of them is, so the cyclotomic polynomials with the dth cyclotomic polynomials where d divides n. So n divides n, so it's a factor as well. And so the remaining factors are the products of dth cyclotomic polynomials where d is less than n, and the factor of n. All right, so by induction hypothesis, f of x has integer coefficients and is monic, right? We assumed that the dth cyclotomic polynomial has integer coefficients if d is less than n, and all of these guys are dth cyclotomic polynomials where d is less than n. So the product of polynomials with integer coefficients has integer coefficients, right? So we use the induction step there. And then f of x is a factor of x to the n minus 1, right? As polynomials in Q of x, right? So first of all, since f of x has integer coefficients and x to the n minus 1 has integer coefficients, we know that in the ring of polynomials with rational coefficients, f of x divides x to the n minus 1. And this is the division algorithm. The division algorithm states if you have a polynomial ring with coefficients in a field, and then you can divide with remainder uniquely, right? And in this case, yeah. So in this case, this gives us, since we have that unique division with the division algorithm, and we also have this as an equation, that means that phi n of x is also a polynomial with rational coefficients. And then by the Gauss lemma, and since f of x is monic, so f of x has integer coefficients and is monic. X at n minus 1 has integer coefficients and is monic, right? Then we know that f of x divides x at n minus 1 as polynomials with z coefficients. So the Gauss lemma relates division of polynomials with rational coefficients to division of polynomials with integer coefficients. The condition for the Gauss lemma is that the polynomials you started with already had integer coefficients and they were primitive. I think it's called primitive polynomials, or like the coefficients of these polynomials have GCD 1. And that is the case because they're both monic. So now using Gauss lemma, we get that f of x divides x to the n minus 1 with in this polynomial ring with integer coefficients. So now that this cyclotomic polynomial has integer coefficients. So are there any questions about this proof? Right. So we proved that the nth cyclotomic polynomial has integer coefficients using induction and Gauss lemma. Right. Okay. Now I'm going to prove that it is also irreducible monic polynomial. And this is the key. So okay, the proof idea is a fun idea. Like the trick is to reduce mod p, and I'm going to explain it. But the point is, the corollary of this theorem is that now you know that this nth cyclotomic polynomial is irreducible, and that means that the minimal polynomial of a primitive nth root of unity is actually this nth cyclotomic polynomial because it's irreducible, right? Okay, so first let's prove that it's irreducible and then get the corollary. Being the thing that we wanted to show that, yeah, we'll get to that. So first, let's prove that the nth cyclotomic polynomial is irreducible. All right, so again, the trick is to reduce mod p. So I'll explain this, but all right. So suppose that the nth cyclotomic polynomial is reducible. So it's a product of two polynomials, which are monic with integer coefficients. Right, we already know that this guy has integer coefficients. So that's the reason why we prove this lemma. We prove this lemma showing that phi n has integer coefficients so that we can use it in this proof to show that it's irreducible and use the mod p trick, right? Once you have integer coefficients, you can reduce mod p, right? Okay, so suppose it's reducible. So it's a product of integer polynomials, integer coefficient polynomials, and say the first factor f is irreducible, right? So we're trying to do this by contradiction. We're trying to prove that phi n is irreducible. So suppose it's reducible, and say it factors as a product of an irreducible polynomial and some other polynomial. So f of x is irreducible, and let zeta be a root of f of x, right? So one thing to note is that zeta is a root of f of x, and therefore it's a root of the nth cyclotomic polynomial, and the nth cyclotomic polynomial is a product, is a polynomial which has primitive nth roots as its roots, right? So zeta is a primitive nth root of unity. And then let p be, all right, sorry about the background noise, but so let p be a prime not dividing n. Okay, so this is what we're going to use in the trick when we reduce mod p. So we're just letting p be any prime, not dividing n, which the n is the thing we're taking the nth roots of. We're taking nth roots of unity. So zeta to the p is a primitive nth root of unity. So why is this the case? Because p is a prime not dividing n, so p is co-prime to n, first of all, and zeta is a primitive nth root of unity. So you raise a primitive nth root of unity to a power which is co-prime to n, you get another primitive nth root of unity, right? I talked about this earlier. So zeta to the p is a root of f of g or f of x or g of x, right? Because phi n of x has all of its roots being all of the primitive nth roots of unity. If zeta to the p is a primitive nth root of unity, it's also a factor of this guy. So it's either a factor of this guy or a factor of this guy. Okay, so suppose that it's a factor of this guy, right? We're gonna get a contradiction. So suppose zeta to the p is a factor of g of x. So g of zeta to the p equals 0, right? So zeta is a root of the polynomial g of x to the p. Since f of x is the minimal polynomial of zeta, so, right, we assume that f of x is irreducible and it has a root being this primitive nth root of unity. So what happened? So yeah, zeta is a root of this irreducible polynomial, and this polynomial has integer coefficients. So it's the minimal polynomial for zeta. And also zeta is a root of g of x to the p, right? So by definition of minimal polynomial, we know that f of x divides g of x to the p, and all of these have integer coefficients. So this is division in the polynomial ring with integer coefficients. So now we get this thing. So in other words, you can write g of x to the p as a product of f of x times h of x, where h is another polynomial with integer coefficients. And now we're going to reduce mod p. Right. So this is a polynomial relation with integer coefficients, and reducing mod p, we get this thing in the field with coefficients in fp, finite field of p elements. And then from Eric's lecture last time, we know that if you take a polynomial with coefficients in fp of x to the p, that's the same thing as a polynomial raised to the p, right? So this is a Frobenius automorphism, right? Raising to the pth power commutes, but it is actually a field automorphism, right? So yeah, yeah. So this polynomial is the same thing as this polynomial, and now we're going to use the fact that fp of x is a unique factorization domain. So what does this mean? So now f of x, f bar of x, and g bar of x have a factor in common in this polynomial ring with coefficients in the finite field, right? What we did was we shown this relationship, and then since this is a unique factorization domain, when you like take all of the irreducible factors on this side and irreducible factor decomposition on this side, you're going to see that f of x and g of x have some factors in common, right? Okay, so now that means that so the conclusion out of all of that was that f bar of x and g bar of x have a factor in common over this this field, finite field fp, as polynomials with coefficients in fp. All right, now let's take a step back and remember that we factored the assumed to be reducible cyclotomic polynomial as a product of an irreducible and some other polynomial. And now we reduce mod p here, and we get that when we reduce mod p, we get this reduced equation. And from this line right here, we see that f bar of x and g bar of x have a factor in common, that means that phi bar n of x, this reduced nth cyclotomic polynomial, has a multiple root, right? So yeah, this f bar has a factor in common with g bar, so you actually get, if you factor this, if you look at how this splits in the splitting field, it's going to have an it's going to have a monomial factor which is repeated at least twice. So that means that the nth cyclotomic polynomial with reduced coefficients has a multiple root. And then this guy is a factor of this guy. So that means x to the n minus 1 with in the polynomial ring with coefficients in FB has a multiple root. Okay, so lots of, there's a whole long chain of logic, but the end result is a contradiction, right? So x to the n minus 1 has n distinct roots over a field of characteristic not dividing n. This was also from the last section. But we concluded that it has repeated roots. So this contradicts the fact that it has distinct roots. So all of that was to show was that our assumption that zeta to the p is a root of g cannot be true. So zeta to the p must be a root of f. And remember, right, zeta is a root of, zeta is a root of f, p is a prime not dividing n, and zeta to the p is another root of the original polynomial, so it has to be a root of g or of f. We showed it can't be of g, so it has to be a root of f. So all of this is to conclude, where are we? So all of this is to conclude that zeta to the p is a root of f of x. We started with zeta as a root of f. Now we know that zeta to the p is a root of f, where p is some prime not dividing n. And this applies to every root of f. So zeta to the a is a root of f for every integer relatively prime to n. So let's see why this sentence is true. So write a, I think this is supposed to be a. Let me get correction. Right, so this is a. Where are we? So this is a. And a has a prime factorization. A has a prime factorization, a product of not necessarily distinct primes. And using the logic above, zeta to the p is a root of f. So starting with zeta as a root of f, we conclude that zeta to the p is a root of f. We know that zeta to the p1, so this first prime factor, is a root of f. And then using this as a root of f, we know that this to the p2 is a root of f, right? Just by using that logic. Zeta is a root of f implies zeta to the p is a root of f, where p is relatively prime to n. And so we repeat this process to get another root of f, and then repeat this process again until you get zeta to the p1 to the p2 to the p3 all the way to the pk. So essentially zeta to the a, right? So zeta to the a is a root of f. So for every integer a relatively prime to n. And what this means is that every primitive nth root of unity is a root of f of x. But we know that the nth cyclotomic polynomial is the product of all of these x minus primitive nth roots of unity, right? So actually, what we showed is that f of x is equal to the nth cyclotomic polynomial. And f of x was assumed to be irreducible, so that's how we prove that the nth cyclotomic polynomial is also irreducible. All right, so that was a long proof. Are there any confusions about this proof? Or is it all good? Okay. So now the last part, I'm going to answer the question. Right. So the original question was like, the original question that we were trying to answer is, what is the degree of this extension? So you take Q, right? You take Q and then you extend it by a primitive nth root of unity, zeta n, and you want to know what is this degree. And the proposed answer was that it's 5n. So how do we show this? Well, basically, it's just the minimal polynomial of this primitive nth root of unity is actually the nth cyclotomic polynomial. Why? Because it's a root of the nth cyclotomic polynomial. By definition, all of the primitive nth roots of unity are roots of the nth cyclotomic polynomial. And we just showed that it's irreducible. So it's an irreducible polynomial with coefficients in Q, actually it has coefficients in Z, and it has zeta n as a root. So this is the minimal polynomial, and the degree of the minimal polynomial is 5n, right? Is the number of integers less than n relatively prime to n, right? So that shows it. That shows that the degree of this extension is the degree of the minimal polynomial, which is 5n. So as a conclusion, we get corollary 42. Right, and let me just write this out. It says the degree, this degree, zeta n over Q is 5n. Right. Okay, so we're done with section 13.6. Actually, there's one more example I could show you. So let me just do this example. So the example is, we're looking at the cyclotomic field Q adjoin the eighth primitive root of unity. And then recall that phi of 8, well, how many factors are there of 8? How many relatively prime numbers are there to 8? So we have 1, 2, 3, 4, 5, 6, 7, and 8. This is not relatively prime. This is not relatively prime. This is not. This is not. This is. So is that 3? No, it should be 4. Oh, 1 is relatively prime, right? Yeah, I guess 1 should count as relatively prime. Okay, so there are 4 relatively prime integers to 8. So phi of 8 is 4. And so we expect that this, the degree of this extension should be 4 over Q. Well, we proved it, so it has to be, right? And also, this field contains the 4th roots of unity. So, hold on. The 4th roots of unity are Q adjoin I, right? I to the 4th is equal to 1. And yeah, there are 4 fourth roots of unity, 1, -1, I, and -I, and they're all in this field, so this contains all of them. And then this is over Q. And we already know that it's also true that this field contains Q adjoins square root of 2. Well, why? Well, the claim is that zeta 8 plus zeta 8 to the 7th is equal to square root of 2. Yeah. I guess we could just carry out this thing, zeta 8 to the 7 squared. We get zeta 8 squared plus 2 times zeta 8 times zeta 8 to the 7th is 1. So 2 times 1 plus zeta 8 to the 14th. So you get here you get what? So this is like -2 because 14 is like -2 mod 8. Right, 16 minus 2 is 14. And then zeta 8 squared plus zeta 8 minus squared. Yeah, these should cancel each other out. They should be additive inverses. And then you get 2. Right, because this is a primitive fourth root of unity. So it's either going to be plus minus 1 or plus minus I, right? And then the inverse of this guy is going to be the negative of whatever fourth root of unity is. So these two things cancel each other out. So this would be minus plus 1 or minus plus I. And so they cancel each other out and you just get 2. So this thing is a square root of 2. So we get Q adjoins square root of 2 as a subfield. But both of these have degree 2, right? So that means that we conclude that Q adjoin zeta 8 is just the composite of these two subfields. So square root of 2 and I. So yeah, the 8th cyclotomic field is the field that you get by adjoining square root of 2 and adjoining I. Okay, so that's all. Any questions? All right, I'll stop the recording.